Hello, everyone. Let's get started. Welcome to How to Use Google Cloud Storage to Unify Your Data for Analytics Workloads. If you care about data-intensive apps and object storage, you're in the right place. If you're not, I won't be offended. Let's get started. So my name is Vivek Saraswat. I have my colleague, Brad Kelemen. We're from the Google Cloud Storage Product Management team. And we have our special guests, our customers from Uber, Henry Gray, Senior Manager, and Abhi, Khune, Principal Engineer, who have both been instrumental in migrating Uber's analytical platform to the cloud. So a quick flash for our agenda. We'll start by talking about the motivations and the rationale for unifying analytics data. We'll talk about the cloud storage data platform and how it helps you to drive this vision. We'll talk about some of the key challenges involved in unifying your data, as well as some of the capabilities that we've released or are announcing for addressing these challenges. Our friends at Uber will give a deep dive into their journey to the cloud for their analytics workload and the challenges in their partnership with Google Cloud. And then finally, we'll have time for a panel Q&A for you to ask us any questions. So one of the key trends today in the analytics and the infra space is the idea of the data lakehouse, which means taking a combination of different data types, so structured data or unstructured data, in order to support multiple workloads and user types. Could be BI, could be AI and data science. And the workloads can come from application sources. They can come from batch and streaming, ingestion, and analytics. And unifying them all into one interface with a unified table format. For example, Apache Iceberg or Hoodie or Delta Lake. And then all applying that with a consistent security and governance model. And the goal here is, again, that unified interface for all of your analytics workloads and for all of your user types. And so that's a great vision. But this is a storage session. And in reality, you might have the unified interface on top. But when you get into the storage details, you often end up with data silos. So if you have many different types of workloads with different performance and semantics characteristics, they might need different storage types, like local SSD or persistent disk or object storage. They might need different interfaces, for example, file-like semantics. And the data might be located in different regions, different continents, for compliance reasons and also for performance, for co-location of storage and compute. All of this leads to data silos, which means multiple copies of the data in different locations. Having multiple data copies means that you might have data that's out of sync or unavailable to the user. And you might have inconsistent security models because you're using different storage types, which might have different security platforms. All of this leads to increased cost and complexity, which starts to blunt some of that analytics lakehouse vision. So our goal is to help you unify your data on Google Cloud Storage. What that means is storing your data once, accessing it anywhere with any performance and any interface and at any scale. Let's dive into this a little bit as to what that means. So if you're creating a unified data platform for analytics, we're going to start at the bottom of this slide with utilizing cloud storage as your unified storage layer. Customers love cloud storage as an object storage platform. Customers love it because it's simple. It's a single global API endpoint. It is reliable, 12 nines durability and up to 4 nines availability. And it's cost effective. We have customers running this at the petabyte scale and beyond. Now, with that single unified layer of storage, you can have different types of data, structured data like Avro or Parquet, semi-structured data like JSON or XML, and unstructured data, image, text, video that you might find in AI/ML use cases, for example. All of that combined data serves the analytics pipeline and tooling process. So ingesting your data, processing the data, managing the metadata for insights, and then security for actually governing the data. With the tooling that you have, you can support many different types of workloads, whether they're based in Google Cloud directly, whether they're utilizing partner vendor analytics services, or whether you're running an open source platform like Hadoop, Spark, or Kafka, or any combination thereof. And then that all supports the use cases that you're actually driving for the end user: BI, querying, streaming analytics, data science, and machine learning. So this is how you create that unified data platform. And you might think, look, Vic, this is a great vision, but of course, there's a lot of challenges involved. And there are, so let's dive into those. We'll start with performance. So if you're doing analytics querying, you need fast time to answers. That means you need high throughput. And since you might have compute in different regions and locations, you need the ability to run those workloads anywhere and ensure that you have local performance with that compute. From a governance standpoint, you need to ensure that you've got fine-grained access control at all levels of your hierarchy. And you need to make sure that you have that you integrate with your existing tool sets. from a programmability standpoint, let's think of this as how your applications actually interface with your storage. You might need to think about the semantics you're using. For example, data teams are used to working with local file systems. And you might need to figure out how you optimize this unified storage system to meet the demands of the application. So think about Hadoop-like applications that expect hierarchical behavior and performance. And then finally, you need to support all the workloads. So from an ecosystem perspective, that means supporting first-party optimized cloud provider services. You might need partner services for multi and hybrid cloud. And then you might have self-managed applications like proprietary workloads or open source. So now we're going to start diving into some of these challenges. I'm going to turn it over to Brad to talk about performance.
Thanks, Vivek. So if you're running data-intensive workloads, performance is absolutely critical to you. We know this, and we give you a way to store once and run anywhere. In order to store once and run anywhere, you need to solve the data location dilemma. I show here 2 examples of customers struggling with the data location dilemma. If you're a national retailer, you have many petabytes of data with users across a continent looking to access the data. If you're a social media company like Snap or Midjourney, you have many petabytes of data with users running daily ML training workloads against that data, and they're looking to access GPUs and TPUs. All of these examples have 4 ways they can go about solving the problem. One is they can move the data, but that's expensive and time-consuming. Another is they can create copies of the data. Again, it's expensive to maintain copies all over the place. And you run the risk of creating data islands and serving out-of-sync data from the various copies. You can choose to access the data across the network path, leave it in where it is. But then you have latencies and the network costs associated with the long network paths. And then even if you can do any of these things, any of these other 3 things, you may not know what data is hot and where to move it to. So how do you go about solving this location dilemma? Well, first you need to look at where you're going to put the data. You can put it in a regional bucket. The regional bucket is great, it's low cost, but it only gives you easy access from one region. You can put it in a dual region bucket. Now you can access it easily from 2 regions, but again, that's somewhat limited. You can go with the most flexible choice and put it in a multi-region bucket, which is a Google Cloud Storage unique product. And this is very flexible, but you still have to traverse a long network path. So now what do? You use anywhere cache with multi-region bucket. This allows you to store once and run anywhere across the continent. The anywhere cache is a zone local SSD-backed read-only cache. If you look at the diagram on the right, you'll see that we have a multi-region bucket with caches on the West Coast, the Midwest, and the East Coast. On your first read, the bucket egresses the data to your VM and simultaneously fills the data into the cache. And subsequent reads of that data come from the cache, which is in the same zone as your VM. The anywhere cache is easy to enable. It's just a bucket setting. It automatically scales to what you need. There's no need to provision terabytes of data that you may not use. And it works with your existing APIs. No need to change refactor your code or move it to a new bucket. It works with existing buckets. Finally, it serves only consistent reads. If you've got multiple caches, all the caches will serve consistent data. If the underlying data is updated, the cache will serve a miss, retrieve the data from the bucket automatically, and refresh the data in the cache. So when would you want to use it? You want to use the anywhere cache in order to get fast time to answers and efficiently use your compute resources. The anywhere cache can serve up to 10 terabits per second per cache. This means if you have 4 caches enabled, for example, on a bucket, that bucket can get 40 terabits per second from all the caches in aggregate. This is far more than you can get from most other caches. The anywhere cache is also well suited for large data sets. Again, it exceeds the capacity of almost any other cache out there. You can put up to 1 petabyte of data in each anywhere cache. The anywhere cache reduces your cost because it's automatically scaling. You only pay for what you use. You don't need to provision 10 terabytes of data if you're only caching 5 terabytes of data. If you are reading 5 terabytes of data, you pay for 5. And if you go up to 10, it goes up, you pay for up to 10. And if you go down to 2, it goes down to 2. Because it's avoiding a long network paths, you avoid the network egress fees, so you save in that way too. The anywhere cache will not serve inconsistent data, so you don't need to worry about setting up a cache with local SSD or your own cache cluster, and then having to keep that fresh all the time. We ensure that all the cache data in the cache is consistent. Finally, it's very easy to implement. You just enable it with a bucket setting, and the workloads will run seamlessly without any changes. So how do you go about using it? There's 4 steps to using an anywhere cache. First, you do discovery, then you do create, and you monitor and you manage. In discovery, we provide a recommender tool to help you understand where to run the caches and what settings to use. This recommender tool simulates caching on your bucket for your past 7 days. Then you can also, after you're done with discovery, you do create. And then once your buckets, your caches are created on your bucket, then you monitor the caches for the benefit and for troubleshooting. And then finally, you manage. So let's take a look at how this works in action. Here's a demo to show you how it works.
The bucket list. The anywhere cache works with multi-region, dual region, or single region buckets. When setting up a cache, you choose the bucket that has the source data, and the cache location should be in the same zone as your VM. I have enabled the cache status column. If you want to configure a cache, you can click on the cache status. This takes you to the configuration screen. Here you can see the zones in which you can create caches. If you are unsure whether a cache will help, you can see recommendations by selecting zones with light bulb icon. The recommender performs cache simulations based on your past 7 days of usage. The recommendations are based on 3 metrics. The first metric, the cache hit rate, shows the percentage of bytes that would have been served from the anywhere cache had it been enabled. This gives you an indication of the likelihood of your workload being accelerated. The second metric shows your potential cost savings by using the anywhere cache. If you are using a multi-region bucket, you are paying network data transfer fees to read data from that bucket. Using the anywhere cache allows you to avoid those fees for data read from that bucket. In this example, we also see almost about $6,000 per week of savings. The cache also provides a lot of extra throughput. The last metric shows that the cache would have served almost 900 gigabits per second of peak throughput. The recommender also gives you an estimated cost. In this case, we see that the cost would have been about $1,400 a week. The metrics and the cost are based on the time to live setting. The recommender simulates multiple TTLs and picks the lowest cost one. I'm showing 1 day here. Once you pick a zone, you can accept the recommended TTL or change it. You can change it anywhere between 1 hour and 7 days. The TTL is the time since last access. Another important setting is the ingest on second access setting, which is over here on the right. It's a great way to reduce cache cost. In many cases, if you use the second access setting, you will only lower the hit rate a small amount while decreasing the cache cost by a lot. After selecting the zones, I'll select 2 here. You can save the configuration. A long-running operation starts to create the caches. It takes about 40 minutes to create the caches. Meanwhile, I'll go to a bucket that I've already created caches. And when you're done creating caches, you can go to the observability tab in the bucket page and you can see the total number of caches enabled here is 2. If you look at the graphs, you see the graph on the left, the cache hit rate over time shows the cache hit rate over time, while the graph on the right shows the amount of data being ingested into the cache over time. Scrolling down, we see the cache hit throughput and the cache miss throughput over time. After observing the behavior of your caches, you may want to take action to manage the cache. From this screen, we'll go back up, you can edit the configuration. You may want to pause the cache. Pausing a cache causes data ingestion into the cache to stop while allowing the data already in the cache to continue to be read. This feature is useful for troubleshooting. For instance, if you have a rogue process, it's a convenient way to isolate the problem. It's also a way to isolate important hot data from other data. Scan the important data into the cache, then pause the cache to prevent less important data from being ingested into the cache. Finally, you can tear down a cache or disable it here.
All right. So the last thing I want to talk about in terms of performance is a new API that we have called GRPC. GRPC is a great way to reduce your time to answers and improve your utilization of your compute. It gives you lower latency and reduced overall execution time when compared to JSON API. It's available in C++, Java, and Go client libraries. You can also use it with the cloud storage connector if you have a Hadoop or Spark workload, including if you're using Dataproc. Finally, if you're using Dataflow, it works with the cloud storage pipelines. All right, and now turning it over to Vivek to talk about governance.
Thank you, Brad. All right, so let's talk a little bit about governance. So really, the important topic for a lot of folks here is how you can lock down your data, and particularly with fine-grained access control. Let's start with some customer examples. So let's say you're a communication service provider like Verizon or AT&T. You have a multi-tenant analytics platform that's using Dataproc, our partner service, for managing Spark Analytics workloads. They really want to be able to manage partitions to tables and to manage permissions, to tables and partitions that are stored in cloud storage buckets, and ensure that each tenant has access only to specific pieces of data. Now, you can use IAM permissions to help you lock down the data in a consistent manner, but bucket-level granularity is often not enough when you have highly partitioned workflows that might have lots of folders or lots of rows and columns within their tables. So how do you solve that problem? We're happy to announce Managed Folders, a new GA capability within cloud storage that provides fine-grained IAM control. So a managed folder is a resource that enables IAM permission grants for a group of objects with a common prefix. So for example, you can set it to A/B/, and all objects that have that prefix will be managed by that IAM grant policy. Examples of how this can be used are setting access to tables and partitions, for example, in a structured data format, or if you have unstructured data, you can think about it as just setting a permission on a folder. This works in existing buckets, no app code changes required. And we've also added a folder browser in the UI, which you can see on the right, which allows you to see a good hierarchical view of how your cloud storage environment looks like. If you happen to be using BigQuery and you want to provide the same IAM policy, you can actually do that directly through BigQuery through fine-grained row column IAM and policy tags. And that allows you to provide access control for BigQuery managing Big Lake or cloud storage external tables. So no matter what your top source of data is, you can be able to provide fine-grained access control at any level. Let's move to programmability. So we mentioned before, programmability is really about how your applications interface with your storage. And in particular, I'm going to talk about optimizing your storage with file-oriented behavior and semantics. So if you've used object storage in the past, you'll know that object storage is a flat namespace. That means that all the objects sit within one layer. And when you see folders in your cloud storage UI or CLI, they're actually just simulated by prefixes. So if you have an object called A/object1, A/ shows up as a folder, but it doesn't actually exist. There's no resource backing it. That can cause issues for applications that need file-like behavior. We'll take the example of an autonomous software provider, for example, Neuro or Cruise, that's using cloud storage buckets as the primary repository for ML training and operations. So data scientists often expect with their tooling local file system semantics, not object storage ones. What that means in this case is that the users need to download their data locally to their laptop or local environment or to their VMs, iterate on the model, and then upload the data back to the bucket. And that can lead to reduced utilization of compute. So how do we help solve this? We have a capability called Cloud Storage Fuse. Cloud Storage Fuse enables you to mount a bucket as a local file system on your client. So when you mount it on the client, it starts looking like folders and files, although the bucket itself is still a flat namespace. What that means is that you can iterate on the data directly from your buckets without having to downloading it, reducing compute idle time. And Cloud Storage Fuse, it's GA. It's really easy to deploy via Linux package or with integrations with products like GKE, Vertex AI, and deep learning. And brand new at Next, we've announced the new GA Fuse File Cache, which allows you to use a local directory as a cache to accelerate reads, particularly for small and random IOs. And that means you can load data faster. This can lead to, our tests have shown 59% faster training time or 58% TCO savings. So Cloud Storage Fuse is a great solution for putting on top of a bucket and exposing it with file-like semantics. However, the bucket itself is still flat, and so that can lead to performance issues. So let's take the example of a software service provider that's migrated their data analytics platform to Google Cloud. And examples include Uber and Activision Blizzard. They run Hadoop ecosystem tooling, and Hadoop ecosystem tooling like Hadoop and Spark generally expects HDFS, so it expects a file-optimized behavior. That can lead to certain issues when you're using something like a flat namespace, like object storage. Let's take the example of a common Hadoop processing task is when you run a Hadoop job and you're running tasks, it takes all the files, puts them in a temporary folder, processes all those files, and then renames the folder to a final destination. In a file system, that rename just works, the folder's renamed, and it's fine. In object storage, since that folder doesn't actually exist, what's happening is every object below that prefix is copied and deleted and moved to under the new prefix. But that means if you have, say, hundreds or thousands of objects, at any given time, you don't know whether this rename operation is completed and whether the objects have moved and the folder have moved from the source destination to the source folder to the destination folder. So the rename isn't atomic. Another problem is, let's say you're trying to list all the folders in list the folder hierarchy at any point in the bucket. Today, in object storage, you have to do a list object call on every prefix, get the prefixes below, do list object calls on all of them until you've mapped out the entire folder hierarchy. So all of this can lead to inefficiency, resiliency, and consistency issues. So how can we actually optimize the bucket to start looking more hierarchical? That's why we're really excited to announce today the upcoming preview for hierarchical namespace buckets. Hierarchical namespace buckets are a new bucket creation option which optimizes the storage layout. So instead of a flat namespace, you have folders, and you have folders and objects that sit within those folders and backed by API resources. And this is really aimed at file-oriented and data-intensive workloads. So one example of how this helps is improved throughput. So if you use cloud storage today, there's a certain QPS limit that initially starts for reads and writes, and then that limit scales up linearly as your workload ramps up. The storage layout enhancements in HNS buckets allow you to have up to 8x initial bucket QPS for object read and write operations, which means you can get your application started faster and you can get them scaling more quickly. We've also added file system-like enhancements, so a new folder resource with APIs that you can manage, and a rename folder API that does atomic renames of the folder and everything below it. And this really enables that atomic folder use case that we talked about before. There's also a list folders API, which allows you to list out the folder hierarchy at any point within the bucket. And finally, if you need to do fine-grained IAM, you can use the managed folders feature that we talked about before and attach the permissions at a folder anywhere in the hierarchy. And if you rename that folder, the permissions will travel with it. This is all compatible with our existing ecosystem. So it supports the object storage API. We support the cloud storage connector and Dataproc for Hadoop and Spark workloads. And if you want a more file-like environment on your client, you can use Cloud Storage Fuse on top of the HNS bucket. So now I'm going to turn it back to Brad to talk about ecosystem.
Thanks, Vivek. All right. We all know everybody has the ecosystem that they're working in, and it's very hard to change ecosystems. So We provide a platform that works with any ecosystem, and you choose the tools. Whether you're running with Google first-party products like BigQuery, Dataproc, and Dataflow, or you're using partner products like Databricks, Commvault, or Palo Alto Networks, or if you roll your own using open source Hadoop, Spark, or PyTorch, cloud storage provides a single source of truth for all of them. All right, now we've got Henry, who works with the engineering team at Uber, and he's going to show you how they're using these various products and features to build their solutions.
All right, thank you, Brad. So hi, everyone. I'm here from the Uber engineering team to talk about how Uber is working with GCP to power our mission to enable users to go anywhere and get anything at the click of a button. GCP have been fantastic partners throughout this journey, so I'm excited to talk more about this today. So first off, some context on Uber's batch data platform. So this is a massive platform that's used every day by internal users at Uber, and it's critical to Uber's day-to-day business. We support half the company using the platform every week, which brings with it a lot of personas using the platform, and with them a wide range of workloads. We support 8 million queries a week and 100,000 active pipelines. And we started migrating this platform to GCP in January 2023. And we already have over 100 petabytes onboarded. Prior to this, we were a typical internet scale company leveraging the Hadoop ecosystem for our data lake. So why are we doing this migration? The first reason is to simplify operations. By working with GCP, we're able to substantially simplify our supply chain management, as well as hardware management. We're unable to unlock new capabilities. In 2009, when Uber was founded, the Hadoop ecosystem was a natural fit for Uber, and it scaled well for us over the last 10 plus years. But we're starting to hit scaling limits now. And those scaling limits are not just software related, we're also hitting hardware related issues. For example, some of the specialized HDFS configurations we have are getting harder and harder to buy. And the last one is to increase productivity. The less Uber engineers are worrying about issues with infrastructure, the more they can focus on higher impact engineering work for Uber. So this is a simplified view of our data lake on GCP, what we refer to as Cloud Lake. At the top here, you can see the different workloads we support. So from dashboards, automated reporting, ad hoc analysis, and developing and running machine learning models. So to power those, we have multiple data tools that we've categorized here into BI tools, orchestration, and metadata platform. And to power this entire platform, we capture event data into Kafka and ingest that into the storage layer in Data Lake. The storage layer here has replaced HDFS with Google Cloud Storage, but we've maintained the Parquet and Hoodie table and file formats that we use with HDFS. On the right, we have our security layer, which I'll talk a little bit more about in a minute, but that's powered by Kerberos, Auth, and Token Broker. We have batch analytics provided by Spark and Presto, and real-time analytics powered by Flink and Pinot. And all of this utilizes Yarn and Kubernetes for compute. So in this next section, I'll talk about some of the challenges we've had to overcome as part of this modernization effort. The first one was, how are we going to maintain HDFS performance parity? Before we started this, the general consensus was that we couldn't do this. But GCP assured us we could and worked with us on multiple initiatives last year to make that reality. For example, when we started doing some initial testing with a pre-GA version of the GRPC GCS connector, we saw a lot lower performance than with the JSON client. But now, after working with Google engineers, we have performance parity between them, which has given us a huge bump in performance. We worked with GCP on enabling parallel composite uploads, which has given us substantial improvements as well, seeing as much as a 40% improvement in write throughput. We've worked on Spark optimizations together, adding observability to enable more fine-tuning for our Spark workloads. And we're not done yet. There's more to do. We're very glad to hear about the HNS buckets that Vivek just mentioned. We started doing some initial beta testing with that, and we're excited about the performance improvements and consistency gains that will bring. The next big question is, how do we do this migration without impacting the users of the platform, which are the other Uber internal employees? As mentioned, they use this every day for their day-to-day operations. So we've done a lot of work here to make sure that that Google Cloud Storage looks the same as HDFS to users of the data platform. So the first thing we did is we standardized and mandated all HDFS clients within Uber into one official version. And that enabled us to provide just one API for connecting to HDFS and GCS. We created a new service called Data Mesh, and this does a lot of the heavy lifting, hiding the differences between HDFS and GCS. For example, it manages the mapping of the differences between HDFS files and folders and objects and buckets. It's how we ensure we apply access controls at the right level of the storage hierarchy so that we don't hit hard limits. And it's also how we implement policies for things like org-level governance. We also had a deep partnership with GCP on creating a whole new security layer that we call Storage Access Service. And this bridges the gap between the Hadoop security model and the GCP's IAM model. This is based on GCP's token broker code base, and it allows us to use Kerberos to manage GCS resources. And the last big challenge I'll talk about is how are we going to do this multi-year migration while maintaining an on-prem and a cloud footprint. So the first thing is we had to do a lot of detailed planning to ensure the optimal pairing of storage and compute workloads so that we had local reads and writes. We created a new service that not only automatically copies and verifies data between on-prem and cloud, but also proxies workloads based on the location of the data they require. So that as we're onboarding more and more to cloud, where workloads are running and where their data resides is transparent to users of the platform. And the last one is capacity planning. We've done a lot of detailed capacity planning with GCP so that we know down to the core per week level when capacity is coming up on cloud. So that gives us confidence to know that as we're decommissioning capacity on-prem, the corresponding capacity is available on cloud. This avoids us paying the double bubble tax and embraces a philosophy we refer to internally as hugging the curve, referring to the on-prem mission curve. So to wrap up, by working with GCP, we're modernizing our open source data lake. We're doing this while maintaining performance expectations, avoiding a painful migration for our users, and utilizing existing on-prem capacity until end of life. And with that, back to Brad.
All right. Thanks, Henry. So you can see we've helped you run your data-intensive workloads by addressing your primary concerns regarding performance, governance, programmability, and ecosystems.